Tonight, we're going to explore one of the most humbling questions in all of astronomy. How much of the universe have we actually seen? Not how much exists, but how much can we observe? How much light has reached our telescopes? How much of reality we've actually been able to glimpse? The answer is going to challenge everything you think you know about our place in the cosmos. You might think we've mapped the universe, catalogued the galaxies, seen what's out there. We haven't. Not even close. By the end of tonight, you're going to understand why we live in a universe where most of what exists will remain forever invisible to us, separated not by distance alone, but by the fundamental structure of space-time itself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. When you look up at the night sky, what you're seeing is a tiny sliver of reality. The stars you can see with your naked eye, all 7,000 or so of them from the darkest locations on Earth, represent an almost infinitesimally small fraction of what's out there. Every single one of those stars is in our immediate cosmic neighborhood. The farthest naked eye star is only about 16,000 light-years away. That sounds far, and it is by human standards. But our galaxy alone is roughly 100,000 light-years across. So even the most distant star you can see without a telescope is still within our own galaxy, still part of our local stellar neighborhood. The entire night sky you've ever experienced, every constellation, every planet, every meteor, every visible star, all of it exists within a bubble roughly 30,000 light-years across. That's about 30% of the Milky Way's diameter. And the Milky Way is just one galaxy. There are hundreds of billions of galaxies in the observable universe, each one containing hundreds of billions of stars, most of which we'll never see individually, we'll never catalogue, we'll never know anything about. But let's start with what we can see. Let's build up from our immediate surroundings to the edge of the observable universe, tracking what becomes visible as we gain better tools and understanding. With your naked eyes on a perfectly clear, dark night, far from any city lights, you can see approximately 7,000 stars, maybe 8,000 if you have exceptional vision and patience. This number has been known since ancient times. Ptolemy catalogued 1,022 stars in the 2nd century. Hipparchus before him catalogued slightly fewer. The exact count varies depending on atmospheric conditions, light pollution, and individual eyesight. But it's always in the thousands, never the tens of thousands. You can also see the Andromeda Galaxy. It appears as a faint, fuzzy patch in the constellation Andromeda. To the naked eye, it doesn't look like much, just a dim smudge. Ancient astronomers catalogued it as a nebula, a cloud of gas within our own galaxy. They had no idea it was an entirely separate galaxy, 2.5 million light-years away, containing 1 trillion stars. On certain nights, you might see the large and small Magellanic Clouds if you're in the southern hemisphere. These are dwarf galaxies orbiting the Milky Way, about 160,000 and 200,000 light-years away, respectively. They appear as hazy patches of light, like pieces broken off from the Milky Way itself. And of course, you can see planets. Mercury, Venus, Mars, Jupiter, and Saturn are all visible to the naked eye and have been known since ancient times. They appear as bright points of light that move against the background stars over nights and weeks. Ancient astronomers tracked them carefully, noting their complex paths across the sky. That's it. That's everything visible to the naked eye. 7,000 nearby stars, a handful of planets, one distant galaxy, and a couple of satellite dwarf galaxies. That's the sum total of the universe humans experienced for all of recorded history until the invention of the telescope. The invention of the telescope around 1608 changed everything. Galileo Galilei turned his telescope toward the sky in 1609 and immediately began seeing things no human had ever seen before. He saw that the moon had mountains and craters, that Jupiter had 4 moons orbiting it, that Venus showed phases like our moon, that Saturn had strange appendages on either side that later observers would recognize as rings. But perhaps most importantly, he saw stars, thousands of stars invisible to the naked eye. When he pointed his telescope at the Milky Way, that faint band of light crossing the sky, it resolved into countless individual stars. What had appeared as a glowing cloud was actually the combined light of millions of distant suns too faint to see individually without optical aid. As telescopes improved over the following centuries, astronomers saw more and more. They catalogued nebulae, fuzzy patches of light scattered across the sky. They discovered Uranus in 1781, extending the solar system beyond Saturn. They found asteroids, comets, and eventually Neptune in 1846, based purely on mathematical predictions of where an unknown planet should be to explain irregularities in Uranus's orbit. By the early 20th century, astronomers had catalogued hundreds of thousands of stars and thousands of nebulae, but they still didn't know the true scale of the universe. They didn't know if those nebulae were gas clouds within the Milky Way or separate galaxies far beyond our own. They didn't know how large the Milky Way was or where Earth sat within it. They didn't know if the Milky Way represented the entire universe or if it was just one island of stars in a much larger cosmos. The debate reached a climax in 1920 when 2 prominent astronomers, Harlow Shapley and Heber Curtis, held what became known as the Great Debate. Shapley argued that the Milky Way was enormous, hundreds of thousands of light-years across, and that the spiral nebulae were relatively small gas clouds within our galaxy. Curtis argued that the Milky Way was smaller, tens of thousands of light-years across, and that the spiral nebulae were separate galaxies, island universes comparable in size to our own Milky Way. The answer came in 1923 and 1924 when Edwin Hubble used the most powerful telescope in the world, the 100-inch Hooker telescope on Mount Wilson in California, to observe the Andromeda Nebula in detail. He identified individual stars within Andromeda, including a class of variable stars called Cepheid, variables whose brightness varies in a regular, predictable pattern. These Cepheid variables are incredibly useful because their period of variation, how long it takes them to go from bright to dim and back to bright, is directly related to their intrinsic brightness. Measure the period, and you know how bright the star actually is. Compare that to how bright it appears from Earth, and you can calculate its distance. Hubble's measurements showed that Andromeda was roughly 900,000 light-years away. Later refinements would revise this to about 2.5 million light-years, but the fundamental conclusion remained the same. Andromeda was far beyond the Milky Way. It was a separate galaxy. And, if Andromeda was a separate galaxy, then so were the other spiral nebulae scattered across the sky. The universe suddenly became much, much larger. Instead of one galaxy, hundreds of thousands of light-years across, there were countless galaxies spread across distances, millions of light-years apart. The Milky Way wasn't the universe. It was just one galaxy among many. Over the following decades, astronomers catalogued more and more galaxies. They found galaxies in every direction, at every distance they could observe. Nearby galaxies, a few million light-years away. Distant galaxies, hundreds of millions of light-years away. The numbers grew astronomical. Millions of galaxies became tens of millions, then hundreds of millions. Today, with modern telescopes, we've catalogued billions of galaxies. The Hubble Space Telescope alone has observed hundreds of thousands of galaxies in deep field images, tiny patches of sky photographed over many hours or days to capture the faintest, most distant objects possible. The most famous of these is the Hubble Ultra Deep Field, an image of a region of sky so small it would fit behind a grain of sand held at arm's length. In that tiny patch, Hubble detected 10,000 galaxies. Some of them, so distant their light, has been traveling toward us for over 13 billion years. Let me put that in perspective. The Hubble Ultra Deep Field covers an area of sky about 1/13 of the Moon's diameter. If you were to look at the full Moon and imagine dividing it into 169 equal squares, the ultra-deep field would cover one of those squares. It's incredibly tiny. From Earth, it's about 2.5 arc-minutes across. That's 2.5/60ths of a degree. To capture this image, Hubble pointed at this tiny patch of apparently empty sky for a total of 11.5 days of exposure time, spread over 4 months in 2003 and 2004. The telescope took 800 separate exposures, each one between 20 minutes and an hour long. These exposures were then combined into a single deep image. The result was breathtaking. In what appeared to the naked eye, and even to smaller telescopes, as empty black space, Hubble revealed 10,000 galaxies. Some of them are large, bright, and relatively nearby, just a few 100 million light-years away. Others are tiny, faint, and incredibly distant. The most distant galaxies in the ultra-deep field appear as they were when the universe was only about 800 million years old. That's less than 6% of the universe's current age. These are among the first galaxies to form after the Big Bang. We're seeing them as they were in the universe's infancy. Many of these galaxies are small and irregular. They haven't yet developed into the grand spiral or elliptical structures we see in nearby galaxies. They're still in the process of forming, still accumulating mass through mergers and accretion. They're cosmic teenagers, young and chaotic and full of rapid star formation. But the Hubble Ultra Deep Field was just the beginning. In 2009, Hubble imaged an even smaller, even darker patch of sky, creating the Hubble Extreme Deep Field. This image covered only about half the area of the ultra-deep field, but went even deeper. Hubble observed this region for a total of 23 days of exposure time. The result was an image containing over 5,500 galaxies in an area even smaller than the ultra-deep field. Some of these galaxies existed when the universe was only 450 million years old. We're seeing light that has been traveling toward us for over 13.3 billion years. Think about what that means. These photons left their parent galaxies when the universe was 3% of its current age. They've been traveling through expanding space for 13 billion years. During that time, the galaxies that emitted them have evolved, merged with other galaxies, formed trillions of new stars, possibly developed intelligent life. But we're seeing them as they were over 13 billion years ago. The light we're observing is ancient beyond comprehension. When these photons began their journey, the universe was barely recognizable compared to today. There were no spiral galaxies like the Milky Way. Most galaxies were small, irregular, and actively forming stars at tremendous rates. The cosmic web, that large-scale structure of filaments and voids that characterizes the modern universe, was just beginning to form. And all of this incredible data came from imaging a region of sky that would be covered by a pinhead held at arm's length. If we extrapolate from the Hubble deep fields to the entire sky, we get those estimates of 200 billion to 2 trillion galaxies in the observable universe. But there's significant uncertainty in these numbers. The faintest galaxies detected in the E-extreme deep field are right at the limit of what Hubble can see. They're so faint that they're barely distinguishable from background noise. Astronomers have to use sophisticated statistical techniques to determine which faint blobs are real galaxies and which are just random fluctuations in the background. And there's good reason to think even fainter galaxies exist below Hubble's detection limit. The distribution of galaxy brightnesses seems to continue to fainter levels. For every bright galaxy we see, there are 10 or 100 fainter ones. This trend seems to continue as far down as we can observe. The James Webb Space Telescope is now finding some of these fainter galaxies. Launched in December 2021, JWST observes in infrared light. This is crucial for seeing the most distant galaxies because their light has been redshifted by cosmic expansion from visible light into the infrared. A galaxy that emits blue light, when that light is emitted, will appear red or even infrared by the time it reaches us. If the galaxy is distant enough, this is because the expansion of space stretches the wavelength of light as it travels. The farther the light travels, the more it gets stretched, the more it gets redshifted. Hubble observes primarily in visible and ultraviolet light, with some infrared capability. But JWST is optimized for infrared, allowing it to see galaxies that are invisible to Hubble. In its first year of operation, JWST discovered numerous galaxies more distant than any Hubble had found. Galaxies that existed when the universe was only 200 million to 400 million years old. These are closer to the Big Bang than any galaxies we'd seen before. Some of these early galaxies are surprisingly bright and massive. This has been a puzzle for astronomers. Theoretical models predicted that the first galaxies should be small and dim. They should be building up mass gradually through mergers and accretion. But some of the galaxies JWST is finding are quite massive for their age. This suggests that galaxy formation in the early universe was more efficient than we thought. Stars formed faster, galaxies assembled their mass more quickly, and structure developed earlier than predicted. It's forcing astronomers to revise their models of early cosmic history. This is exciting. It's exactly what you want from a new telescope. Not just confirmation of what we already think we know, but surprises that challenge our understanding and force us to think harder about how the universe works. But even JWST has limits. There are galaxies too faint and too distant for even JWST to detect. There are regions of the observable universe we simply cannot see with current or any foreseeable technology. Consider the cosmic dark ages. This is the period after the cosmic microwave background was emitted, about 380,000 years after the Big Bang. But before the first stars formed, roughly 150 million to 200 million years later. During this period, the universe was dark. There were no stars, no galaxies, no light sources at all except the fading glow of the cosmic microwave background. The universe was filled with neutral hydrogen gas, slowly collapsing under gravity into the regions that would eventually form galaxies. we cannot directly observe this period. There's no light from this era because no stars had formed yet. The cosmic microwave background tells us what the universe looked like before the Dark Ages. The first galaxies tell us what it looked like after. But the Dark Ages themselves are invisible. We can infer what was happening during this time using theoretical models and computer simulations. We can calculate how the hydrogen gas should have been distributed based on the tiny density fluctuations we see in the cosmic microwave background. We can simulate how those fluctuations grew under gravity. We can predict when and where the first stars should have formed. But we can't observe it directly. This is a fundamental limitation. The Dark Ages were dark because there was no light. And if there's no light, we can't observe them with telescopes. There are proposals to detect the Dark Ages indirectly by observing the 21-centimeter line of neutral hydrogen. This is a radio emission from hydrogen atoms that occurs when the electron in the atom flips its spin. During the Dark Ages, the universe was full of neutral hydrogen, and this hydrogen should have emitted 21-centimeter radiation. If we could detect that radiation, we could map the distribution of hydrogen during the Dark Ages and watch the universe's structure evolve during this hidden period. But this is incredibly difficult. The signal from the Dark Ages has been redshifted by cosmic expansion from 21 centimeters to several meters wavelength. It's also very faint, buried under much stronger foreground signals from our own galaxy and from radio interference on Earth. Astronomers are trying. Radio telescopes specifically designed to detect 21-centimeter radiation from the Dark Ages are being built. The most ambitious is the Square Kilometre Array, an international project to build the world's largest radio telescope, with a total collecting area of 1 square kilometre spread across thousands of individual antennas in Australia and South Africa. But success is not guaranteed. The technical challenges are immense. And even if we succeed in detecting the signal, we'll only be mapping the distribution of hydrogen gas. We won't be seeing individual objects or structures in the way we see galaxies in visible light images. So there are periods of cosmic history and regions of space that are fundamentally difficult or impossible to observe directly. We can infer what happened. We can build models and simulations. But we can't see them the way we see galaxies in Hubble images. If you take the number of galaxies detected in the ultra-deep field and scale it up to cover the entire sky, you get an estimate of roughly 200 billion galaxies in the observable universe. That's 200 billion separate collections of stars, each one containing anywhere from tens of millions to trillions of stars. More recent estimates from data collected by the Hubble Space Telescope and other observatories suggest the number might be even higher. Some astronomers think there could be as many as 2 trillion galaxies in the observable universe. The uncertainty comes from the faintest, most distant galaxies, which are extremely difficult to detect and count accurately. But here's the key thing to understand. All of these galaxies, all 200 billion or 2 trillion of them, exist within what we call the observable universe. This is not the same as the entire universe. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It's a sphere centered on Earth, with a radius of roughly 46 billion light-years. Wait, you might be thinking, how can the observable universe have a radius of 46 billion light-years if the universe is only about 13.8 billion years old? Shouldn't light have only had time to travel 13.8 billion light-years? This is where things get counterintuitive. The universe has been expanding since the Big Bang. Light that was emitted from a distant galaxy 13 billion years ago has indeed been traveling for 13 billion years. But during that time, space itself has been expanding. The galaxy that emitted that light has moved farther away due to the expansion of space. Today, that galaxy is roughly 46 billion light-years away, even though its light has only been traveling for 13 billion years. This expansion also means that the most distant objects we can see are not the oldest objects in the universe. The cosmic microwave background, the afterglow of the Big Bang, is the oldest light we can detect. It was emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could travel freely through space. That light has been traveling toward us for about 13.8 billion years. But the regions of space that emitted that light are now about 46 billion light-years away due to expansion. So, the observable universe is a sphere 46 billion light-years in radius, containing somewhere between 200 billion and 2 trillion galaxies, each containing hundreds of billions of stars. That's what we can see. That's what light has had time to reach us from. But what about beyond the observable universe? What exists out there in regions so distant that light hasn't had time to reach us yet? The honest answer is we don't know for certain. But we have good reasons to think the universe extends far beyond what we can observe. In fact, based on our best cosmological models, the universe might be infinite. Here's why. When we measure the geometry of space using observations of the cosmic microwave background and the distribution of galaxies, we find that space is remarkably flat. What does flat mean in this context? In geometry, there are 3 possible shapes for 3-dimensional space. It can be positively curved, like the surface of a sphere, where parallel lines eventually converge. It can be negatively curved, like a saddle shape, where parallel lines diverge. Or it can be flat, like an infinite plane, where parallel lines remain parallel forever. Our measurements show that space is flat to within about 1% uncertainty. This flatness has profound implications. If space is truly flat, and not just approximately flat, then it must be infinite. A flat, finite space would have edges or boundaries, and we see no evidence of such boundaries. An infinite universe means that beyond the edge of our observable universe, there's more space, more galaxies, more stars, stretching on forever in all directions. Everything we can see, all 2 trillion galaxies, all their hundreds of billions of stars, all the planets and gas clouds and black holes and nebulae, all of it is just an infinitesimal fraction of what exists. But even if the universe is infinite, we can only ever observe a finite portion of it because of the speed of light and the expansion of space. Light travels at 186,000 miles per second, but that's still finite. Given the age of the universe, 13.8 billion years, there's a maximum distance from which light could have reached us. That distance defines the edge of the observable universe, and that edge is moving. Every year that passes, light from slightly more distant regions has time to reach us. The observable universe is growing. But it's not growing fast enough to catch up with the expansion of space. Here's where it gets truly strange. The universe isn't just expanding. It's expanding at an accelerating rate. This acceleration is driven by something we call dark energy, a mysterious form of energy that permeates all of space and causes space to expand faster and faster over time. Because of this accelerating expansion, there are galaxies that are currently moving away from us faster than the speed of light. This doesn't violate relativity. Nothing is moving through space faster than light. But space itself is expanding so rapidly that the distance between us and these galaxies is increasing faster than light could traverse it. Light from these galaxies can still reach us if it was emitted long ago when those galaxies were closer. But light being emitted from them now will never reach us. The expansion of space is carrying them away too quickly. By the time that light has traveled part way toward us, the expansion of space has stretched the remaining distance even farther. The light is like a person running on a treadmill that's speeding up faster than they can run. They can run forward, but they're being carried backward faster than they're advancing. This creates what's called the cosmic event horizon. It's similar to the event horizon of a black hole, but instead of being a boundary in space, it's a boundary in space-time. Beyond this horizon, events happening now will never be observable from Earth, no matter how long we wait. The light from those events will never reach us because the expansion of space prevents it. The cosmic event horizon is currently about 16 billion light-years away. That's much smaller than the 46 billion light-year radius of the observable universe. Remember, the observable universe includes light from regions that are now 46 billion light-years away. But that light was emitted when those regions were much closer, before the expansion had carried them so far. The event horizon, by contrast, represents the farthest distance from which light emitted now could ever reach us. Galaxies beyond about 16 billion light-years, as they exist now, will never be visible to us. We can see them as they were in the past, when they were closer, but we can't see them as they are now, and we never will. As time goes on, and the universe continues to expand and accelerate, this event horizon will actually shrink. Galaxies that are currently just within our cosmic event horizon will cross it and disappear from our view. Not because they're destroyed, or because their light is redshifted into invisibility, but because the expansion of space has carried them beyond the boundary from which light can reach us. In the very far future, hundreds of billions of years from now, only the galaxies in our immediate local group will remain visible. Everything else will have been carried beyond our cosmic event horizon by the expansion of space. An observer in that distant future will look out at the universe and see only the local group, a small cluster of a few dozen galaxies surrounded by empty space. They'll have no way to know that there were once trillions of other galaxies beyond. All evidence of those galaxies will have disappeared beyond their cosmic horizon. Let me paint you a picture of what this distant future looks like in more detail. Imagine you're an astronomer 1 trillion years from now. The Milky Way has long since merged with Andromeda and several other local group galaxies to form a giant elliptical galaxy. Let's call it Milkomeda. When you look out from this merged galaxy, you see a few dozen satellite galaxies nearby. These are the gravitationally bound companions that never had enough energy to escape the local group's gravity. Together, they form an island of light in an otherwise dark universe. Beyond this small cluster, you see nothing. No distant galaxies. No quasars. No cosmic web of filaments and voids. Just darkness. You can't see the cosmic microwave background anymore. After 1 trillion years of expansion and cooling, it's been redshifted so far into the radio spectrum that it's indistinguishable from background noise. You have no evidence that the universe began in a hot, dense state. You have no evidence of the Big Bang. If you measure the Hubble constant by observing how the local group satellite galaxies move, you'll find that they're not moving away. They're orbiting Milkomeda or moving randomly. You'll conclude that the universe is static, not expanding. You'll have no way to discover dark energy. No way to know that the vast majority of the universe's energy density comes from something causing space to accelerate apart. All that evidence has disappeared beyond your cosmic horizon. You might measure the masses of galaxies and find they have more mass than can be accounted for by visible stars and gas, so you might discover dark matter. But you'll have a much smaller sample of galaxies to study, making it harder to understand dark matter's properties, and you'll have no way to know that the universe is much older than your galaxy. If you measure the ages of the oldest stars in Milky, you might find stars 10 billion years old, left over from the pre-merger Milky Way and Andromeda, but the universe itself is 1 trillion years old by this point. You'll likely conclude that the universe is only 10 billion years old, missing the vast majority of cosmic history. Essentially, most of what we know about cosmology today would be undiscoverable. The expansion of the universe, the Big Bang, dark energy, the cosmic microwave background, the existence of trillions of other galaxies, all of it would be hidden. This thought experiment illustrates something profound. The knowledge we can gain about the universe depends on when we exist in cosmic history. We're fortunate to live at a time when the universe is old enough that we can observe its large-scale structure, but young enough that the evidence hasn't yet been carried beyond our horizon by expansion. In the universe's very early history, for the first few 100 million years, there were no planets, no life, no observers. The universe was too hot and dense for complex chemistry. In the very far future, after hundreds of billions or trillions of years, there might be observers, but they'll have access to much less information about the universe. Most of the evidence we can see today will be gone. We live in what might be called the golden age of cosmology, a brief window in cosmic history, maybe 10 billion years long, when observers can study the universe's large-scale structure and history. Before this window, no observers existed. After it closes, observers might exist, but won't be able to learn what we know. This makes our current knowledge precious. We're the ones who can see the full picture, or at least more of it than future civilizations will. We have a responsibility to record what we've learned, to preserve this knowledge for any future observers who might not have access to the same evidence. And it also makes you wonder about what we might be missing. Are there aspects of the universe that were observable in the past but are no longer accessible? Evidence that existed when the universe was younger but has since been erased by cosmic evolution? Probably yes. The very earliest moments after the Big Bang, the first fraction of a second, produced conditions and physics that no longer exist anywhere in the observable universe. The energy densities and temperatures were so high that matter behaved in ways we can never directly observe. We can theorize about what happened. We can build models based on particle physics and quantum field theory. We can run experiments in particle colliders that recreate some of the conditions, though not the extreme conditions, of the very earliest moments. But we can't directly observe the first instant of the Big Bang. That information is lost. The universe has evolved too far from that initial state. Similarly, there might be evidence of events that happened in the universe's first few 100 million years that's no longer accessible. The first stars that formed and then exploded as supernovae. The first black holes that formed and then merged. The first galaxies that assembled and then got disrupted by mergers. Some of this history might be preserved in the oldest stars, in the chemical abundances they contain, in the structure of dark matter halos, but much of it is lost. We can infer what happened based on our understanding of physics and our observations of later epochs, but we can't see it directly. So, Even within our observable universe, even within the cosmic horizon that bounds our view, there are things we can't observe because they happened too long ago, and the evidence has been erased by subsequent evolution. This is another form of cosmic invisibility. Not things that are too far away to see, but things that are too far in the past to observe directly. The universe has a finite age. Information from before the Big Bang, if such a concept even makes sense, is inaccessible. And information from the universe's earliest moments has been scrambled and diluted by 13.8 billion years of cosmic evolution. We're reading a book where the first pages are missing, and the rest have been partially erased and overwritten many times. We can make out the general plot. We can understand the major themes. But some of the details are lost forever. This is already happening, in a sense. There are galaxies we can see now as they were in the distant past, but that we're seeing for the last time. Their light from more recent epochs will never reach us. We're observing the final photons that will ever arrive from certain distant regions of space. This raises a profound question. If there are parts of the universe we can never observe, regions forever beyond our cosmic event horizon, can we really claim to understand the universe as a whole? We've built our cosmological models based on what we observe within our observable universe. We assume that the universe is homogeneous and isotropic, meaning it looks roughly the same in all directions and at all locations. This is called the cosmological principle, and it's fundamental to our understanding of cosmology. All the evidence we have supports this principle. Wherever we look, we see galaxies distributed in similar patterns. The cosmic microwave background looks the same in all directions to within 1 part in 100,000. The laws of physics appear to work the same way everywhere we can observe. But the cosmological principle is an assumption, not a proven fact. We assume the universe beyond our observable horizon is similar to what we see within it. But we can't verify this. There could be regions of space fundamentally different from what we observe. There could be domains where the laws of physics are different, where the constants of nature have different values, where matter and energy behave in ways we've never seen. Some theories of cosmic inflation, the rapid expansion thought to have occurred in the first fraction of a second after the Big Bang, predict exactly this. Inflation suggests that our observable universe is just one region in a much larger multiverse, a vast space that underwent inflation. Different regions of this multiverse might have different properties, different laws of physics, different numbers of dimensions. If this is true, then our observable universe is like a bubble in an infinite foam. Each bubble has its own properties, its own laws, its own history, and we can only ever observe our own bubble. The other bubbles are forever beyond our reach, separated not by distance that could in principle be crossed, but by the fundamental structure of space-time itself. So how much of the universe have we actually seen? If the universe is infinite, then mathematically, we've seen 0%. Any finite number, no matter how large, is 0% of infinity. All the galaxies we've catalogued, all the stars we've observed, all the cosmic structure we've mapped, it's all infinitesimally small compared to an infinite universe. If the universe is finite, but much larger than our observable universe, we've seen a tiny fraction. Maybe 1%, maybe 1/1000%, maybe even less. We don't know, because we can't measure how large the total universe is. But even within our observable universe, we haven't seen everything. We've catalogued billions of galaxies, but we haven't catalogued all of them. The faintest, most distant galaxies are still beyond our current instruments. The James Webb Space Telescope, launched in December 2021, is finding galaxies that Hubble couldn't detect. These are galaxies at the edge of the observable universe, so distant and so faint that only the most sensitive instruments can find them. And we certainly haven't catalogued all the stars. The 2 trillion galaxies we estimate exist in the observable universe contain roughly 1 billion trillion stars total. That's a 1 followed by 21 zeros. 1,000 billion stars. We've catalogued perhaps a few billion stars individually. Most of the stars, in even nearby galaxies, remain anonymous points of light, blended together in the glow of their parent galaxy. As for planets, we've only scratched the surface. We've detected about 5,000 exoplanets. As of 2024, planets orbiting stars other than our Sun. But estimates suggest there are at least as many planets as stars in our galaxy alone. That would mean roughly 400 billion planets in the Milky Way, and that's just one galaxy. In the entire observable universe, there could be 10 billion trillion planets or more. We've seen essentially none of them directly. Let me explain how we detect exoplanets and why it's so difficult. The vast majority of known exoplanets have been found using the transit method. This involves watching a star very carefully and looking for tiny, periodic dips in its brightness. If a planet orbits the star, and that orbit is oriented such that the planet passes between us and the star, the planet will block a tiny fraction of the star's light. This creates a dip in brightness that repeats every orbital period. The Kepler Space Telescope, which operated from 2009 to 2018, used this method to discover over 2,600 confirmed exoplanets and identify thousands more candidates awaiting confirmation. Kepler stared at a single patch of sky containing about 150,000 stars and monitored their brightness continuously for years. When a star showed repeated dips in brightness at regular intervals, that was a sign of a transiting planet. By measuring the depth of the dip, how much the star dimmed, astronomers could calculate the size of the planet. A deeper dip means a larger planet blocking more light. By measuring the period between dips, they could calculate the planet's orbital period and therefore its distance from the star. But the transit method only works if the planet's orbit happens to be aligned such that it passes between us and its star. For a randomly oriented planetary system, the chance that we'll see transits depends on the planet's orbital size. For a planet in an Earth-like orbit around a Sun-like star, the probability is only about 0.5%. That means, for every 200 planetary systems like ours, we'll only see transits from one of them. For larger orbits, the probability is even smaller because the planet has to be precisely aligned across a larger distance. For smaller orbits, the probability is higher, but then you're mostly seeing hot Jupiters and other close-in planets. This means that the planets we detect via transits are not representative of all planets. We're biased toward finding large planets in close orbits because these create the biggest, most frequent dips in starlight. Small planets in large orbits are much harder to detect. Earth, orbiting the Sun at 1 astronomical unit, causes the Sun's brightness to dim by roughly 84 parts per million, once per year, when viewed from the right angle. That's a change of 0.0084%. And this dip lasts only about 13 hours each time. Detecting this from light years away requires incredibly precise measurements and long-term monitoring. You need to measure a star's brightness to an accuracy better than 100 parts per million. You need to monitor the star continuously for years to catch multiple transits and confirm they're periodic. and you need to rule out other causes of brightness variations like star spots, which are like sunspots, but on other stars. Kepler could do this. It was specifically designed for this purpose. But it could only monitor a limited patch of sky. And even within that patch, it could only detect planets whose orbits happened to be aligned for transits. The Transiting Exoplanet Survey Satellite, or TESS, launched in 2018, is taking a different approach. Instead of staring at one patch of sky, TESS surveys the entire sky, spending about a month observing each region. This allows it to find bright nearby stars with transiting planets, even if it can't monitor any one star for as long as Kepler did. TESS has found thousands of exoplanet candidates, many of them around bright stars that are easier to study in detail with other telescopes. But it's still limited to finding planets that transit. The other major method for finding exoplanets is the radial velocity method, also called the Doppler method. This works by measuring the star's motion. When a planet orbits a star, the star doesn't stay perfectly still. Both the planet and the star orbit their common center of mass. For a massive planet orbiting a lightweight star, this can cause the star to move noticeably. As the star moves toward us and away from us in its orbit, the light from the star gets Doppler shifted. When it's moving toward us, the light is slightly blue shifted. When it's moving away, the light is slightly red shifted. By measuring these shifts very precisely, we can detect the star's motion and infer the presence of a planet. The radial velocity method was the first successful technique for finding exoplanets. The first confirmed exoplanet around a Sun-like star, 51 Pegasi b, was discovered this way in 1995. But this method is also biased. It's most sensitive to massive planets in close orbits because these cause the largest stellar motions. Jupiter causes the Sun to move at about 12.4 meters per second. Earth causes the Sun to move at about 9 centimeters per second. Detecting a motion of 9 centimeters per second from light years away is extraordinarily difficult. It requires measuring Doppler shifts to an accuracy of about 1 part in 100 million. Current instruments can achieve this for nearby bright stars, but it's at the limit of what's possible. So both major detection methods are biased toward finding certain types of planets. Large planets close to their stars are easy to find. Small planets in large orbits like Earth are much harder. This means our catalogue of exoplanets is not representative of all planets. We've found thousands of hot Jupiters, gas giants, orbiting very close to their stars with orbital periods of just days. We've found many super-Earths, planets larger than Earth but smaller than Neptune. We've found some Neptune-sized planets and a few Earth-sized planets in close orbits. But we've only found a handful of planets in Earth, like orbits around Sun, like stars. And we've found 0 planets in Jupiter, like orbits around Sun, like stars, using the transit method, because Jupiter's orbital period is nearly 12 years. You'd need to monitor a star for decades to see multiple transits from a Jupiter analog. Direct imaging of exoplanets is possible, but incredibly difficult. You have to block out the light from the star and then detect the tiny amount of light reflected or emitted by the planet. This only works for young, massive planets that are still hot from their formation and orbiting far from their star. As of 2024, only about a dozen planets have been directly imaged. All of them are giant planets, much more massive than Jupiter, orbiting tens or hundreds of astronomical units from their stars. These are not representative of most planets. So when we say we've detected 5,000 exoplanets, we need to be clear about what that means. We've detected 5,000 planets using methods that are biased toward finding certain types of planets. The actual population of planets in the galaxy is likely very different from what we've catalogued. Statistical analyses of Kepler data suggest that roughly half of Sun-like stars have Earth-sized planets in Earth-like orbits. If that's true, and if there are roughly 200 billion to 400 billion stars in the Milky Way, and maybe 1 in 10 of them are Sun-like, that would mean tens of billions of Earth-like planets in our galaxy alone. We've directly detected maybe a few dozen of them. The rest remain unseen, too small and too far from their stars for our current instruments to find. And that's just in our galaxy. Extrapolate to the entire observable universe with 2 trillion galaxies, and you get numbers that are truly astronomical. 10 billion trillion planets, give or take a few orders of magnitude. Each one a world, each one with its own geology, its own weather, its own history. Some of them likely have conditions suitable for life. Some small fraction might actually have life. An even smaller fraction might have complex life. And who knows, maybe somewhere out there, intelligent beings are looking up at their night sky and wondering the same questions we are. But we'll never catalogue all those planets. We'll never observe them. Most of them are too far away, their parent stars too faint, the planets themselves far too small to detect. We can calculate that they probably exist based on the statistics of what we have found. But we can't see them individually. They remain anonymous, uncatalogued, unobserved. So our catalogue of cosmic objects is woefully incomplete. We've seen a tiny fraction of the stars, an even tinier fraction of the planets, and a vanishingly small fraction of whatever other objects might exist out there. Brown dwarfs, rogue planets, asteroid fields, clouds of gas and dust. Most of it remains unobserved and uncatalogued. But there's another way to think about what we've seen. Instead of asking how many objects we've observed, we can ask how much light we've collected. Every photon that reaches Earth from a distant star or galaxy is information. It tells us something about the object that emitted it. The photon's wavelength tells us about the object's composition and temperature. Its energy tells us about conditions at its source. The direction it came from tells us where to look, and the number of photons tells us how bright the source is. Over the history of astronomy, we've collected countless photons. Every observation, every image, every spectrum represents photons that traveled across space and were captured by our instruments. But how many photons have we actually collected compared to how many have been emitted by all the stars and galaxies in the universe? Stars are incredibly luminous. Our Sun, an average star, emits about 10 to the power of 45 photons every second. That's a 1, followed by 45 zeros, every second. It's been doing this for about 4.5 billion years. That's roughly 1.5 times 10 to the power of 17 seconds. So the Sun has emitted roughly 10 to the power of 62 photons in its lifetime so far. Now, multiply that by the number of stars in the observable universe. 10 to the power of 21 stars, each emitting roughly 10 to the power of 62 photons over their lifetimes. That gives you 10 to the power of 83 photons total, very roughly. How many of those photons have humans collected? Every telescope that's ever been built, every observation that's ever been made, every photon that's hit a detector and been recorded. The largest telescopes on Earth have collecting areas of tens of square meters. They observe for thousands of hours per year. Over the history of astronomy, Let's say we've collected photons using maybe 100 square meters of total collecting area, operating for maybe 100,000 hours total. The number of photons collected would be on the order of 10 to the power of 20. A very rough estimate, but in the right ballpark. So, we've collected about 10 to the power of 20 photons out of 10 to the power of 83 photons emitted. That's one part in 10 to the power of 63. 1/trillionth of a trillionth of a trillionth of a trillionth of a percent. Of all the light emitted by all the stars in the observable universe, we've captured an almost incomprehensibly tiny fraction. Most of the light emitted by most stars will never be observed by anyone. It will travel through space forever, spreading out, redshifting, fading, eventually becoming indistinguishable from the background glow of space itself. This is humbling. We think of astronomy as a comprehensive science, cataloging the cosmos, mapping the universe. But we've barely scratched the surface. We've seen a tiny fraction of what exists, collected an infinitesimal fraction of the light that's been emitted. And there are entire categories of objects we've never seen at all. Black holes, for instance. We've detected them indirectly through their gravitational effects and through the light emitted by matter falling into them. We've even imaged the shadow of a black hole by observing the event horizon's silhouette against the glowing gas around it. But we've never seen a black hole itself. By definition, we can't. It emits no light. Likewise, dark matter. We know it exists because we can see its gravitational effects. Galaxies rotate faster than they should based on the visible matter alone. Galaxy clusters hold together too strongly. Gravitational lensing reveals mass in places where we see no light. All of this points to the existence of dark matter, invisible matter that doesn't emit, absorb, or reflect light. Dark matter makes up about 85% of all matter in the universe. Yet, we've never seen it directly. We've only detected it through gravity. We don't know what it's made of, what particles comprise it, or how it behaves, except through its gravitational influence. So even within our observable universe, most of the matter is invisible to us. We can map its distribution using gravitational effects, but we can't observe it directly. And then there's dark energy. This mysterious component makes up about 68% of the total energy density of the universe. It's responsible for the accelerating expansion of space. But we have no idea what it is. We know it exists because we observe the acceleration. We've measured the expansion rate of the universe at different times by observing distant supernovae and other standard candles. We've found that the expansion is speeding up, not slowing down as you'd expect from gravity alone. Something is pushing space apart, counteracting gravity on cosmic scales. We call this something dark energy, but that's just a name. It's not a theory or an explanation. It's just a label for our ignorance. We don't know if it's a property of space itself, a new kind of field permeating the universe, or something else entirely. So 68% of the universe is dark energy. We don't understand. About 27% is dark matter we can't see. Only about 5% is ordinary matter, the stuff of stars and planets and gas clouds, the stuff we can actually observe with telescopes. And even that 5%, we've only catalogued a tiny fraction of it. This paints a picture of a universe that is mostly invisible to us. Not because it's too far away, though much of it is, but because it's fundamentally undetectable with current technology or even with any foreseeable technology. Dark matter doesn't emit light. We can only detect it through gravity. Unless someone invents a dark matter telescope that can see dark matter particles directly, we'll never observe the bulk of the universe's matter. Dark energy has even less direct impact. We only know about it through its effect on the expansion rate. We might never be able to study it directly. So, when we ask how much of the universe we've seen, the answer depends on what you mean by seen. If you mean directly observed with telescopes, we've seen the light from about 2 trillion galaxies, a tiny fraction of the matter in the observable universe, and an infinitesimal fraction of the total universe if it's infinite. If you include indirect detection through gravitational effects, we've mapped some of the dark matter distribution in galaxy clusters and around galaxies. But we still don't know what it is. If you include the effects of dark energy, we've measured the expansion rate and its acceleration, but we have no idea what's causing it. And if you consider the universe beyond our cosmic event horizon, regions from which light emitted now will never reach us, we've seen 0%. Those regions are forever unobservable. There's something profound and melancholy about this. We're stuck in a small corner of reality, able to observe only a tiny bubble of space around us. Beyond that bubble, the universe extends, possibly infinitely, filled with galaxies and stars and planets and perhaps life, all of it forever beyond our reach. Not just beyond our reach in the sense that we can't travel there, though that's also true, but beyond our reach in the sense that we can't even observe it. The light will never get to us. The information will never arrive. Those regions are as inaccessible to us as the interior of a black hole. In the very far future, this will become even more stark. As the universe continues to expand and accelerate, more and more galaxies will cross our cosmic event horizon and disappear from view. The observable universe will shrink. Not because anything is being destroyed, but because the expansion of space is carrying distant regions beyond the boundary from which light can reach us. Eventually, only the local group will remain visible. Our galaxy, Andromeda, Triangulum, and a few dozen dwarf galaxies, all gravitationally bound to each other. Everything else will have disappeared beyond the horizon. An astronomer in that distant future will look out and see a small cluster of galaxies surrounded by darkness. They'll have no evidence that there were ever other galaxies. The cosmic microwave background will have redshifted into invisibility. All the evidence of the Big Bang, of cosmic expansion, of the vast universe we know exists, will have vanished. They'll live in a universe that appears small and static. They'll have no way to discover the truth about cosmic history, about the Big Bang, about the trillions of galaxies that once existed within their observable universe. All that knowledge will be lost, unless someone in our era records it and passes it down. Unless we preserve the observations and the understanding we've gained during this brief window in cosmic history when the evidence is still visible. This is one reason why astronomy matters. We're living in a unique epoch, a time when the universe is old enough that we can observe distant galaxies and the cosmic microwave background, but young enough that the acceleration of expansion hasn't yet carried everything beyond our cosmic horizon. In a sense, we're lucky. If we'd evolved 1 trillion years from now, we'd have missed our chance to understand the cosmos. We'd be stuck in an observable universe containing only our local group with no way to learn about anything beyond. But we're here now. We can observe the cosmic microwave background. We can see distant galaxies. We can measure the expansion rate and study cosmic history. We have access to evidence that won't always be available. And we've used that evidence to build a remarkably detailed understanding of the universe. We know the universe is 13.8 billion years old. We know it began in a hot, dense state and has been expanding ever since. We know the expansion is accelerating. We know about dark matter and dark energy, even if we don't understand what they are. We know about galaxy formation, stellar evolution, the synthesis of elements in stars, the formation of planets. All of this knowledge comes from studying the tiny fraction of the universe we can observe. From collecting those 1 in 10 to the power of 63 photons, from cataloging a few billion of the 1 billion trillion stars, from observing a few thousand of the 10 billion trillion planets. It's remarkable that we've learned so much from so little, that we've been able to piece together the history and structure of the cosmos from the limited information available to us. But it's also humbling. It reminds us how much we don't know, how much we'll never know, how much exists beyond our ability to observe. There are galaxies beyond our cosmic event horizon that we'll never see. There are stars in those galaxies whose light will never reach us. There are planets orbiting those stars, where, perhaps, life has evolved, civilizations have risen and fallen, questions have been asked and answered. All of it happening in regions of space we can never observe, can never study, can never even know exist. If the universe is infinite, then most of what exists is forever inaccessible. We're confined to a finite bubble in an infinite ocean. Everything beyond that bubble is real, is happening, but is fundamentally unobservable. This challenges the very notion of what it means to understand the universe. If most of the universe is unobservable, can we claim to have a complete theory of cosmology? Can we be confident that the laws of physics we've discovered apply everywhere, even in regions we can never observe? The answer is, we can't be certain. We assume the cosmological principle holds, that the universe is homogeneous and isotropic on large scales. But this is an assumption based on what we observe within our bubble. We have no way to verify it applies beyond. In practice, this doesn't matter much. The region we can observe is vast enough to test our theories and make predictions. And so far, our theories work remarkably well. General relativity describes gravity on cosmic scales. Quantum mechanics describes matter and energy on small scales. The Standard Model of particle physics describes the fundamental particles and forces. These theories make predictions that we can test within our observable universe, and they pass those tests with remarkable precision. One of the most powerful tests comes from the cosmic microwave background, the oldest light in the universe. The CMB was emitted about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, called recombination, the universe was a hot plasma of charged particles. Photons constantly scattered off these charged particles, unable to travel far before being absorbed and re-emitted. The universe was opaque, like being inside a cloud. But when electrons combined with protons to form neutral atoms, photons could suddenly travel freely. The universe became transparent. All the photons that had been trapped in the plasma were suddenly released, streaming through space. These photons have been traveling ever since. As the universe expanded, they were redshifted from visible light to infrared to microwave wavelengths. Today, they fill all of space, coming from every direction with a temperature of about 2.7 degrees above absolute zero. We can detect these photons with radio telescopes. And when we map the sky in microwave wavelengths, we see the cosmic microwave background, a nearly uniform glow covering the entire sky. But it's not perfectly uniform. There are tiny variations in temperature, about 1 part in 100,000. Some regions are slightly hotter, some slightly cooler. These temperature variations correspond to density variations in the early universe. Regions that were slightly denser had slightly higher temperatures. Regions that were slightly less dense had slightly lower temperatures. And these density variations are the seeds that grew into galaxies and large-scale structure. The denser regions attracted more matter through gravity. Over hundreds of millions of years, they collapsed and fragmented into the first stars and galaxies. So, when we look at the pattern of temperature variations in the CMB, we're seeing a snapshot of the early universe. We're seeing the distribution of matter 380,000 years after the Big Bang, before any stars or galaxies had formed. And the pattern matches the predictions of our cosmological models almost perfectly. The size and distribution of the temperature variations tell us about the composition of the universe. How much ordinary matter, how much dark matter, how much dark energy. The overall temperature tells us about the expansion history. The polarization pattern tells us about conditions even earlier, potentially during cosmic inflation. Multiple satellites have mapped the CMB in increasing detail. COBE, in the early 1990s, first detected the temperature variations. WMAP in the 2000s mapped them in detail. Planck, which operated from 2009 to 2013, created the most precise map yet. From these observations, we've determined that the universe is 13.79 billion years old, plus or minus 40 million years. That ordinary matter makes up 4.9% of the universe's total energy density. That dark matter makes up 26.8%. That dark energy makes up 68.3%. That space is flat to within 1%. These are incredibly precise measurements. We know the age of the universe to within about 0.3%. We know its composition to within a few percent. All from studying the pattern of temperature fluctuations in radiation emitted 380,000 years after the Big Bang. The CMB also tells us something profound about the observable universe. It represents the farthest we can see with electromagnetic radiation. Before recombination, the universe was opaque. No photons from earlier times can reach us because they were trapped in the plasma. So the CMB is like a wall at the edge of our observable universe. We can see the radiation from this wall. We can measure its properties. But we can't see through it to earlier times using light. To probe earlier epochs, we need other messengers. Gravitational waves can pass through the opaque plasma unaffected. Neutrinos from the very early universe, if we could detect them, would tell us about the first second after the Big Bang. But with light, the CMB is the oldest thing we can see. And it's coming from every direction. Wherever we look, we see CMB photons that were emitted from the surface of last scattering, the shell of space where recombination occurred. Today, that shell is about 46 billion light-years away in all directions. It's the boundary of our observable universe, but we need to be careful about what this means. The surface of last scattering isn't a physical boundary. It's not a wall or edge in space. It's a moment in time. Imagine space filled with a hot plasma. At a certain moment, everywhere in space, the plasma cools enough to become transparent. That moment happens at the same time throughout space, but we see it at different distances depending on how far the light has traveled to reach us. The CMB photons we detect today were emitted from regions that are now about 46 billion light-years away. But there are CMB photons everywhere in space, including right here where Earth is. The CMB photons currently at Earth's location are flying outward, away from us. An observer 46 billion light-years away in any direction would detect them as their cosmic microwave background. So the observable universe is observer-dependent. Every observer sees a sphere around themselves, 46 billion light-years in radius, defined by the distance light could have traveled since the Big Bang. An observer in a distant galaxy sees a different sphere. It's centered on them, not on us. Their observable universe overlaps with ours, but it also includes regions we can never see, regions beyond our cosmic event horizon. If the universe is infinite, then every point in space is the center of someone's observable universe. There are infinitely many overlapping spheres, each representing what some hypothetical observer could see. Our observable universe, our sphere, is just one of infinitely many. It's not special, except that it's the one we can observe. This is another way of understanding how little we've seen. Even if we catalogue every object in our observable universe, we've only observed one sphere out of infinitely many. An observer far enough away sees a completely different set of galaxies, none of which overlap with ours. Their universe and ours are equally real, equally valid, but they're disjoint. They can never interact, never communicate, never observe each other. The speed of light and the expansion of space ensure they remain forever separate. This is a profound form of cosmic loneliness. We're surrounded by reality we can never access. Not just future events beyond our event horizon, but present events happening right now in regions too far away for their light to have reached us yet. There are galaxies out there, beyond our observable universe, that exist right now. They're real, they're physical, they're full of stars, and perhaps life. But we'll never see them. Their light will never reach us. We're separated by fundamental limits of space-time, and in a sense, they don't exist for us. Not in the philosophical sense of non-existence, but in the practical sense that they can never affect us, we can never observe them, and they're operationally indistinguishable from things that don't exist. If a galaxy exists, but is forever unobservable, does it matter for our understanding of reality? This is veering into philosophy, but it's a question worth considering. Science is based on observation and measurement. We build theories to explain what we observe. We test theories by making predictions and checking them against observations. But if most of reality is unobservable, how can we claim our theories describe reality as a whole? Maybe they only describe the tiny bubble we can observe. Maybe the unobservable regions operate under completely different rules. The counter-argument is that our theories are based on fundamental principles that should apply universally. The laws of physics, as far as we can tell, don't depend on location. Gravity works the same way in distant galaxies as it does here. Electromagnetism has the same strength everywhere we've measured it. Quantum mechanics produces the same effects in distant atoms as in local ones. So we have good reason to think the laws extend beyond what we can observe. But we can't prove it. We can't test it in regions we can never access. It's an assumption, albeit a well-supported one. But we should remain humble about the limits of our knowledge. We've seen a tiny fraction of what exists. We've collected an infinitesimal fraction of the light that's been emitted. We've catalogued a small percentage of the objects in our observable universe, and the observable universe itself might be an infinitesimal fraction of the total universe. So, when someone asks, how much of the universe have we actually seen, the honest answer is, almost none of it. We've seen enough to understand the basic structure and history of the cosmos. We've seen enough to know we live in a vast, expanding universe filled with billions of galaxies. We've seen enough to measure the age of the universe and the rate of expansion. We've seen enough to detect dark matter and dark energy, even if we don't understand them. But we haven't seen most of the matter in the universe, because it's dark matter. We haven't seen most of the energy, because it's dark energy. We haven't catalogued most of the stars or planets or other objects, even within our observable universe. And we'll never see anything beyond our cosmic event horizon. No matter how long we wait or how advanced our technology becomes. This is the reality of our situation. We're observers in a vast, mostly invisible universe. We can see a tiny portion of what exists. We can study that portion in great detail, learning about cosmic history and structure and evolution. But most of reality remains hidden. Not hidden because it's far away, and we haven't looked yet. Hidden because it's fundamentally inaccessible, separated from us by the expansion of space and the finite speed of light. And yet, despite these limitations, we've built a remarkable understanding of the cosmos. We've mapped the observable universe. We've traced cosmic history back to fractions of a second after the Big Bang. We've discovered the laws that govern stars and galaxies. We've found thousands of planets orbiting other stars. We've detected gravitational waves from colliding black holes. We've imaged the shadow of a black hole's event horizon. All of this from our tiny vantage point on a small planet orbiting an average star in one galaxy among trillions. It's a testament to human curiosity and ingenuity, to our ability to ask questions and seek answers, to our willingness to build ever more powerful instruments to probe the cosmos, to our determination to understand our place in the universe, even when that understanding reveals how small and limited we are. We've seen almost nothing of the universe. But what we have seen, we've studied with remarkable care and insight, and we've learned that we live in a universe far stranger and more wonderful than anyone imagined. A universe billions of years old. A universe expanding and accelerating. A universe filled with dark matter and dark energy we don't understand. A universe where most of what exists is invisible. A universe where most of reality is forever beyond our reach. And yet, also, a universe that we can study and understand at least in part. A universe governed by physical laws we can discover and test. A universe that makes sense, that follows patterns, that rewards careful observation and thoughtful analysis. This is the universe we inhabit. Vast beyond comprehension, mostly invisible, mostly inaccessible, but also beautiful and knowable and worth studying. We've seen almost none of it. But what we have seen has changed us forever. It's expanded our horizons, challenged our assumptions, humbled our pride. It's shown us that we're not the center of everything, that we're a small part of something much larger. And it's inspired us to keep looking, keep learning, keep pushing the boundaries of what we can observe and understand. Because even though we've seen almost nothing of the universe, what little we have seen is endlessly fascinating, and there's always more to discover. Tonight, we've explored how much of the universe we've actually seen. The answer is sobering. We've observed a tiny fraction of the objects in the observable universe. We've collected an infinitesimal fraction of the light emitted by all stars. We've catalogued a small percentage of galaxies, stars, and planets. And the observable universe itself is likely just a tiny bubble in a much larger, possibly infinite cosmos. Most of the universe remains invisible to us, not because we haven't looked hard enough, but because it's fundamentally unobservable. Dark matter doesn't emit light. Dark energy is detectable only through its effects on expansion, and regions beyond our cosmic event horizon are forever separated from us by the expansion of space. We live in a universe where most of reality is hidden, where most of what exists will never be seen, never be studied, never be known. This is humbling. It reminds us of our limitations, of how much we don't know and will never know. But it's also inspiring, because despite these limitations, we've learned so much. We've built a detailed understanding of cosmic history and structure. We've discovered laws that govern matter and energy. We've traced the universe from the Big Bang to the present day, all from the tiny fraction we can observe, all from the infinitesimal amount of light we've collected. Imagine what we might learn if we could see more, if we could observe the dark matter directly, if we could study regions beyond our cosmic horizon, if we could collect more than 1 in 10 to the power of 63 photons. We can't do those things. They're beyond the limits of what's physically possible. But we can keep pushing the boundaries of what we can observe. We can build more sensitive telescopes. We can develop new detection methods. We can study the universe in new ways, using gravitational waves, neutrinos, and other messengers that complement light. The James Webb Space Telescope is finding galaxies Hubble couldn't see. Future telescopes will find even fainter, more distant galaxies. Gravitational wave detectors are opening a new window on the universe, letting us observe events that emit no light. Neutrino detectors might reveal processes in the cores of stars and supernovae. Let me tell you about some of these new ways we're observing the universe. Gravitational wave astronomy is barely a decade old, but it's already revolutionizing our understanding of the cosmos. The first detection of gravitational waves came on September 14, 2015, when the 2 LIGO detectors in the United States simultaneously detected a signal from 2 black holes merging about 1.3 billion light-years away. This detection confirmed a century-old prediction from Einstein's general theory of relativity. Einstein predicted that accelerating masses would create ripples in space-time itself, waves that propagate at the speed of light. But he thought these waves would be far too weak to ever detect. He was almost right. Gravitational waves are incredibly weak. The signal detected by LIGO caused the detectors, which are 2.5 miles long, to stretch and compress by about 1/10,000th the diameter of a proton. That's an absurdly small distance. To put it in perspective, if the distance between Earth and the nearest star, Proxima Centauri, 4.24 light-years away, changed by the width of a human hair, that would be a bigger change proportionally than what LIGO detected. The technology required to measure such tiny distances is extraordinary. LIGO uses laser interferometry, splitting a laser beam and sending it down 2 perpendicular arms, 2.5 miles long. The beams reflect off mirrors at the ends of the arms and return to the center, where they recombine. If a gravitational wave passes through, it stretches one arm and compresses the other, causing the beams to get slightly out of phase. This creates an interference pattern that can be detected. But to achieve the required sensitivity, every source of noise has to be eliminated or accounted for. Seismic vibrations from earthquakes, ocean waves, passing cars, even footsteps. Thermal noise from the random motion of atoms in the mirrors and suspension systems. Quantum noise from the fact that light consists of discrete photons that arrive randomly. All of these noise sources had to be reduced to levels below the gravitational wave signal. It took decades of development and refinement. LIGO first began operating in 2002, but didn't detect anything in its initial run because the sensitivity wasn't quite good enough. After a major upgrade between 2010 and 2015, advanced LIGO came online, and within days of starting operations, it detected that first merger. Since then, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events. Most are mergers of black holes, with masses ranging from about 5 solar masses to about 100 solar masses. A few are mergers of neutron stars. One particularly exciting event in August 2017 was the merger of 2 neutron stars that was detected both in gravitational waves and in electromagnetic radiation. This neutron star merger was observed by telescopes across the electromagnetic spectrum. Gamma-ray satellites detected a short gamma-ray burst at the same time and location as the gravitational wave signal. Optical telescopes saw the visible light from the explosion. Radio telescopes tracked the expanding debris. X-ray telescopes observed the hot material. This multi-messenger observation taught us an enormous amount. It confirmed that short gamma-ray bursts, which last only seconds, are caused by neutron star mergers. It showed that these mergers produce heavy elements like gold and platinum through a process called rapid neutron capture, or the R process. It provided a new way to measure the expansion rate of the universe by combining the distance measured from gravitational waves with the redshift measured from the electromagnetic signal. And it demonstrated that we can observe the universe in fundamentally new ways by combining different types of messengers. Light tells us one story. Gravitational waves tell us another. Neutrinos might tell us a third. Together, they give us a much richer picture of cosmic events. Neutrino astronomy is another emerging field. Neutrinos are ghostly particles that barely interact with matter. Trillions of them pass through your body every second from the sun alone, and you never notice because they almost never interact. But occasionally, very rarely, a neutrino will interact with an atom, and if you build a detector large enough and sensitive enough, you can catch these rare interactions. The IceCube Neutrino Observatory at the South Pole is exactly this kind of detector. It consists of over 5,000 optical sensors embedded in about a quarter of a cubic mile of ice deep beneath the Antarctic surface. When a neutrino interacts with an ice molecule, it produces a cascade of particles that emit Cherenkov radiation, a type of light produced when particles move faster than light can travel through the ice. The sensors detect this Cherenkov light and reconstruct where the neutrino came from and how energetic it was. IceCube has detected neutrinos from the sun, from cosmic ray interactions in Earth's atmosphere, and, most excitingly, from distant cosmic sources. In 2017, IceCube detected a very high-energy neutrino and traced it back to a blazar, a galaxy with a supermassive black hole pointing a jet of particles directly at Earth. This was the first time a neutrino had been traced to an extragalactic source. It showed that blazars accelerate particles to incredible energies and that neutrinos can carry information from the most energetic processes in the universe. Future neutrino detectors might observe neutrinos from supernova cores, from the accretion disks around black holes, from the very early universe. Each detection would teach us something we couldn't learn from light alone. Because neutrinos interact so weakly, they can escape from regions where light cannot. The core of a collapsing star is opaque to light. Photons, produced in the core, scatter off electrons and nuclei millions of times before escaping, and this can take thousands or millions of years. But neutrinos can stream directly out of the core. They carry information about conditions deep inside the star that light cannot access. Similarly, the early universe, before it became transparent to light 380,000 years after the Big Bang, was nevertheless transparent to neutrinos. There's a cosmic neutrino background, analogous to the cosmic microwave background, but from an even earlier epoch. We haven't detected the cosmic neutrino background yet because the neutrinos are very low energy and incredibly difficult to catch. But if we could detect it, it would give us a snapshot of the universe when it was only 1 second old, far earlier than anything we can observe with light. These new observational windows, gravitational waves, neutrinos, and in the future, perhaps even more exotic messengers like axions or other hypothetical particles, are expanding what we can see. They're not increasing the volume of space we can observe. We're still limited to the observable universe by the speed of light and cosmic expansion, but they're giving us new ways to probe the regions we can observe. New information about processes and events that don't emit much light or that occur in regions opaque to light. This is crucial because much of the universe is dark. Not dark in the sense of being beyond our cosmic horizon, though that's also true, but dark in the sense of not emitting light. Black holes don't emit light by definition. We can only observe them through their effects on nearby matter or through gravitational waves when they merge. Dark matter doesn't emit light. We can only observe it through its gravitational effects. Neutrinos from most sources don't produce much associated light. We need neutrino detectors to see them. Even ordinary matter is often dark. Gas clouds, too cold to emit visible light. Rogue planets drifting through interstellar space. Brown dwarfs too small to sustain nuclear fusion. Dead stars that have cooled below visible temperatures. All of these exist, but they don't show up in optical surveys. You need infrared telescopes to see cold gas and brown dwarfs. You need careful gravitational surveys to detect rogue planets. You need multi-wavelength observations to build a complete picture. This is why astronomy is increasingly becoming a multi-messenger, multi-wavelength enterprise. No single type of observation tells the whole story. You need optical, infrared, ultraviolet, X-ray, and radio observations to see matter at different temperatures and in different states. You need gravitational wave detectors to see merging compact objects. You need neutrino detectors to see the cores of stars and high-energy cosmic processes. And even with all of these tools, we're still only scratching the surface of what exists. Each new instrument, each new technique expands what we can see, not by much. We'll always be limited by the cosmic event horizon and the finite speed of light. We'll always be observing just a tiny fraction of what exists. But that tiny fraction is worth studying. It's our window into reality, our connection to the larger cosmos. And as long as there are questions to ask and tools to build, we'll keep looking, keep learning, keep expanding our understanding of the universe and our place within it. Let me tell you about some of the largest surveys ever undertaken to map what we can see of the universe. The Sloan Digital Sky Survey, which began operations in 2000, has mapped over 3 million galaxies and quasars. It uses a dedicated 2.5-meter telescope in New Mexico to systematically photograph large areas of the sky, then measure the spectra of interesting objects to determine their distances. SDSS has created a 3-dimensional map of the universe, showing how galaxies are distributed in space. and what it revealed was stunning. Galaxies are not randomly scattered through space. They're organized into an intricate cosmic web. There are vast filaments of galaxies stretching across hundreds of millions of light years. These filaments surround enormous voids, regions of space with very few galaxies. At the intersections of filaments, you find massive clusters containing thousands of galaxies. This large-scale structure, formed through gravity, acting on tiny density fluctuations in the early universe. Regions that were slightly denser than average attracted more matter, over billions of years. This gravitational attraction pulled matter into denser and denser regions, creating the filaments and clusters we see today. The voids aren't completely empty. They contain some galaxies, just far fewer than the filaments, and they're expanding as the denser regions pull matter out of them. The cosmic web extends as far as we can see. Every large survey that looks deep enough finds the same pattern. Filaments, voids, clusters, all organized in a foam-like structure. SDSS and other surveys have mapped this structure out to distances of several billion light-years. They've catalogued millions of galaxies, measured their positions in three-dimensional space, and created maps showing how the universe is organized on the largest scales. But even these massive surveys have only scratched the surface. SDSS has mapped about 1/3 of the sky. It's catalogued 3 million galaxies out of an estimated 200 billion to 2 trillion in the observable universe. That's less than 1%, even using the lower estimate. And SDSS only catalogues relatively bright galaxies. Fainter galaxies below the survey's detection limit remain uncatalogued. There could be 10 or 100 times as many faint galaxies as bright ones. Future surveys will go deeper. The Vera C. Rubin Observatory, currently under construction in Chile, will begin operations in the mid-2020s. It will use an 8.4-meter telescope with an enormous field of view to photograph the entire visible sky every few nights. Over 10 years, Rubin Observatory will catalogue an estimated 20 billion galaxies. That's roughly 10% of the galaxies in the observable universe. If we assume 200 billion total, it will create the deepest, most complete map of the cosmos ever made. But even 20 billion galaxies is just a fraction of what exists. And Rubin, like all ground-based telescopes, will be limited by Earth's atmosphere. The atmosphere blurs images, absorbs certain wavelengths of light, and creates noise that makes it harder to detect faint objects. Space telescopes don't have these limitations. They can achieve sharper images and observe at wavelengths blocked by the atmosphere. But they're expensive and difficult to build and operate. You can only have a few of them operating at once. So there's a trade-off. Ground-based surveys can observe large areas of sky and catalogue millions or billions of objects. But they're limited by atmospheric effects and can't see the faintest objects. Space telescopes can see much fainter and observe at any wavelength. But they have smaller fields of view and can only catalogue smaller numbers of objects. Both are needed to build a complete picture. What these surveys have taught us is that the universe, at least the part we can observe, is remarkably homogeneous on large scales. If you look at any region of the universe, several 100 million light-years across, it looks statistically similar to any other region. The same density of galaxies, the same large-scale structure of filaments and voids, the same types of galaxies in roughly the same proportions. This homogeneity is the basis of the cosmological principle, the assumption that the universe is the same everywhere. and on scales larger than a few hundred million light-years, this seems to be true. On smaller scales, the universe is very inhomogeneous. Galaxies are clustered. Matter is clumped into stars, planets, gas clouds. There's enormous variation from place to place, but zoom out far enough, and it all averages out to uniformity. This is both reassuring and puzzling. Reassuring because it means we can use observations of our local region to draw conclusions about the universe as a whole. If the universe is homogeneous, then studying our cosmic neighborhood tells us about distant regions we can't observe in detail. Puzzling because we have to ask why the universe is homogeneous. What set up these initial conditions? Why didn't some regions have much higher density than others? The answer, according to current theory, is cosmic inflation. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion. Space expanded so quickly that regions that had been in contact, able to equilibrate to the same density and temperature, were suddenly separated by vast distances. Inflation smoothed out any initial irregularities, creating the homogeneous universe we observe today. At the same time, quantum fluctuations during inflation seeded the tiny density variations that later grew into galaxies and large-scale structure. The predictions of inflation match observations remarkably well. The universe is homogeneous to about 1 part in 100,000, exactly what inflation predicts. The pattern of temperature fluctuations in the cosmic microwave background matches the predictions from quantum fluctuations during inflation. The geometry of space is flat, also predicted by inflation. But inflation makes another prediction that's harder to test. If our observable universe underwent inflation, then the region beyond our cosmic horizon likely did too. And inflation theory suggests that different regions might inflate by different amounts, creating a multiverse of bubble universes. Each bubble would have its own properties, possibly its own physical constants and laws of physics. Our observable universe would be just one bubble in an infinite foam. If this is true, then the homogeneity we observe within our bubble tells us nothing about other bubbles. They could be completely different. Some might have stronger gravity, different particle masses, more dimensions of space, and we could never observe these other bubbles. They're separated from us not just by distance, but by the structure of space-time itself. They're as inaccessible as regions beyond our cosmic event horizon. So, even if we could somehow observe every galaxy in our observable universe, catalog every star, map every planet, we'd still only be seeing one bubble in a potentially infinite multiverse. This is speculative, of course. We have no direct evidence for the multiverse. We can't observe other bubbles to confirm they exist. The multiverse might be a mathematical prediction of inflation theory that doesn't correspond to physical reality, but it illustrates how even our most complete possible observations might represent an infinitesimal fraction of total reality. If the universe is infinite and homogeneous, we've seen 0% of it, mathematically speaking. If the universe is a finite but very large bubble, we've seen some tiny fraction. If the universe is one bubble in an infinite multiverse, we've seen an even smaller fraction. No matter how you look at it, most of reality is hidden from us. Not hidden in the sense that we haven't looked yet, or that we need better telescopes. Hidden in the sense that it's fundamentally unobservable, forever beyond the boundary of what any physical measurement could reveal. This is humbling. It puts all of human knowledge in perspective. Everything we've learned, every discovery, every theory, it's all based on studying an infinitesimal sample of reality. And yet, From this tiny sample, we've learned remarkable things. We've determined the age of the universe to within 1%. We've measured the expansion rate to within a few percent. We've mapped the distribution of dark matter through gravitational lensing. We've detected dark energy through its effect on cosmic acceleration. We've traced the history of star formation over most of cosmic time. We've found thousands of planets and determined that planets are common around stars. We've detected gravitational waves and confirmed Einstein's prediction from a century ago. We've imaged the event horizon of a supermassive black hole. All of this from a cosmic sample size that's essentially zero. It suggests that the laws of physics are universal, that the same rules governing matter and energy in our laboratory apply throughout the cosmos, that we can extrapolate from what we observe to regions we can't observe. This is an assumption, but it's a well-supported one. Every test we've performed confirms that the laws of physics work the same way everywhere in the observable universe. Stars in distant galaxies produce the same spectral lines as stars in our galaxy. Gravity works the same way in galaxy clusters billions of light-years away. Radioactive decay rates appear constant across cosmic time, allowing us to date objects reliably. So, even though we've only observed a tiny fraction of the universe, that fraction appears representative. What we learn from it seems to apply generally. We've seen almost none of it. But what we have seen is endlessly wonderful, and there's always more to discover. Let me leave you with some final thoughts about what all of this means. For most of human history, we thought we could see everything. Ancient astronomers believed the stars were on a crystal sphere just beyond the planets. Everything that existed was visible, or so they thought. The invention of the telescope shattered this illusion. Suddenly, there were stars too faint to see with the naked eye, moons orbiting Jupiter, mountains on our moon, countless stars making up the Milky Way. Each improvement in telescope technology revealed more stars, more nebulae, more structure in what had appeared smooth and uniform. The universe kept getting larger and more complex. But there was always the hope, the assumption, that with better telescopes, we'd eventually see everything. That the universe was large but finite, and given enough time and technology, we could catalogue it all. Now, we know that's impossible. Not just difficult, or expensive, or time-consuming. Fundamentally impossible. The cosmic event horizon ensures that we can never see beyond a certain distance. The finite age of the universe and the speed of light ensure we can never observe the entire universe, even if it's finite. If the universe is infinite, as observations suggest it might be, then we're seeing an infinitesimal fraction of what exists. This is a profound shift in perspective. We've gone from thinking we could potentially see everything to knowing for certain that most of reality is forever hidden. And this raises questions about the nature of knowledge and understanding. Can we truly understand something if we can only observe an infinitesimal fraction of it? If someone showed you one grain of sand and asked you to describe Earth's beaches, how much could you really say? You could study that grain in detail, measure its composition, examine its structure, but you'd know almost nothing about beaches in general. You wouldn't know about different types of sand, about beaches made of pebbles or coral. You wouldn't know about tides, about waves, about the interaction between ocean and shore. We're in a similar position with the universe. We have one grain of sand, our observable universe, and we're trying to understand the entire beach. The difference is that our grain of sand is enormous. It contains 2 trillion galaxies, 1 billion trillion stars, 10 billion trillion planets. We can study this sample in great detail, and we've found that it obeys consistent rules. The same laws of physics apply everywhere we look. The same fundamental constants have the same values. The universe appears homogeneous on large scales. So we extrapolate. We assume that what we see in our sample applies to the larger whole. That the laws of physics we've discovered are universal. That the cosmological principle holds. This extrapolation has been successful so far. Every prediction we've made based on our theories has been confirmed by observations. The cosmic microwave background exists and has the predicted properties. Dark matter and dark energy exist and behave as our models predict. The universe's age and expansion rate match our calculations, but it's still an extrapolation from a tiny sample, and we should remain humble about its limitations. There could be aspects of the universe we can't observe because they don't exist in our observable region. Maybe some types of galaxies or cosmic structures only form under conditions that don't occur within our cosmic horizon. Maybe some physical phenomena only manifest on scales larger than our observable universe. Maybe the laws of physics are different in regions we can never access. We have no way to know for certain. Our knowledge is bounded by what we can observe, and what we can observe is bounded by fundamental limits of space-time. This doesn't mean science is futile, or that we should give up trying to understand the universe. It means we should be clear about what we can and can't know. We can study our observable universe in exquisite detail. We can discover the laws that govern matter and energy within this region. We can trace cosmic history back to fractions of a second after the Big Bang. We can predict the future evolution of cosmic structure. All of this is real knowledge, hard-won through observation and analysis. It's incredibly valuable and has transformed our understanding of reality, but it's not complete knowledge. It's knowledge about our observable universe, not necessarily about the universe as a whole. This distinction matters. It affects how we think about cosmology, about the nature of the universe, about our place in existence. If the universe is infinite, then everything that can happen will happen somewhere. Not just similar things, but exact duplicates. There are, mathematically, infinitely many regions of space identical to ours. Infinitely many copies of Earth, of you, of every moment of your life. This seems bizarre, but it's a straightforward consequence of infinity combined with quantum mechanics. If space is infinite and matter is distributed with some finite density, and if quantum mechanics means there are only finitely many possible configurations of matter in any given volume, then every configuration must repeat infinitely many times. It's like flipping a coin infinitely many times. You'll get heads and tails in every possible sequence, including infinitely many sequences of 1 billion heads in a row. In an infinite universe, you must have infinitely many regions identical to our observable universe. Some of them would be identical up to this exact moment, with copies of you reading this exact sentence. Others would differ by tiny amounts, quantum fluctuations that went differently. Still others would differ dramatically, with completely different histories. All of it existing simultaneously, right now, in regions of space we can never observe. This is philosophically strange. It challenges our notions of uniqueness and significance. If there are infinite copies of you, are you still special? Does your life still matter? I would argue yes. The existence of other copies doesn't diminish your experience. Your thoughts and feelings are real to you. Your relationships matter to the people in your life. The fact that similar things might be happening elsewhere doesn't make your life less meaningful, but it does put things in perspective. Anything you do, any discovery you make, any achievement you accomplish has probably been done infinitely many times elsewhere. On the other hand, anything you do that affects the future propagates forward in time in your particular region of space. Your actions have consequences for the specific branch of reality you inhabit. So, in a sense, you matter absolutely to your local region of space-time, even if you don't matter to the universe as a whole. These are deep philosophical questions without clear answers. They emerge naturally from taking our best cosmological models seriously. If the universe is infinite and homogeneous, these implications follow. If it's finite, or if the cosmological principle doesn't hold beyond our observable region, different implications follow. We don't know which scenario is correct. We can't know based on current observations. All we can do is map out the logical consequences of each possibility and acknowledge our uncertainty. What we can say with confidence is that we've observed a tiny fraction of what exists. That most of the universe, however large it is, remains invisible to us. That our knowledge, while impressive and hard-won, is fundamentally limited by the cosmic horizon, and that despite these limitations, we've learned remarkable things. We've discovered that we live in an expanding universe, 13.8 billion years old. We've found that galaxies are organized into filaments and voids on the largest scales. We've detected dark matter and dark energy and mapped their distribution. We've traced the history of star formation and galaxy evolution. We've found thousands of planets and determined that planetary systems are common. We've detected gravitational waves from merging black holes. We've imaged the event horizon of a supermassive black hole. We've mapped the cosmic microwave background and extracted precise cosmological parameters from its tiny temperature variations. All of this from observing our tiny corner of reality. All of this from collecting 1 in 10 to the power of 63 photons. All of this from cataloging less than 1% of the galaxies in the observable universe. It's a testament to human ingenuity and persistence, to our ability to ask deep questions and find ways to answer them, to our willingness to build ever more sophisticated instruments to probe nature's secrets. And it's ongoing. Every year brings new observations, new discoveries, new insights. The James Webb Space Telescope is finding galaxies from the universe's first few 100 million years. Gravitational wave detectors are observing dozens of black hole mergers. Neutrino observatories are opening new windows on high-energy cosmic processes. Radio telescopes are mapping neutral hydrogen across cosmic time. Each new observation refines our understanding. Sometimes it confirms our theories. Sometimes it surprises us and forces us to revise our models, but it always pushes the boundary of knowledge forward. We're living in a golden age of cosmology and astronomy. We have instruments capable of observing the universe in unprecedented detail across the entire electromagnetic spectrum and beyond. We have theoretical frameworks that make precise predictions we can test. We have computational tools that allow us to simulate cosmic structure and evolution. And we have the accumulated knowledge of centuries of observation and analysis to build upon. But we also have to acknowledge the limits of what we can know. Most of the universe is invisible. Most of reality is beyond our reach. Our observations, no matter how comprehensive, only sample a tiny fraction of what exists. This is humbling, but it's also inspiring, because it means there's always more to discover. Always more questions to ask. Always more mysteries to explore. We'll never run out of cosmic puzzles. The universe is too large, too complex, too full of surprises. Every answer leads to new questions. Every observation reveals new phenomena to investigate. Every discovery opens new frontiers. And that's beautiful. That's what makes science exciting. The knowledge that we're exploring a cosmos far stranger and more wonderful than we ever imagined. That we're part of something vast and ancient and ongoing. So, when someone asks, how much of the universe have we actually seen? The answer is almost none of it. But what we have seen is spectacular. And the quest to see more, to understand more, to push the boundaries of knowledge ever outward, that quest continues. It will continue as long as there are humans looking up at the night sky and wondering what's out there. As long as there are scientists building telescopes and analyzing data. As long as there are curious minds asking questions about the cosmos. We may never see most of the universe, but we'll never stop trying to see more. Thanks for joining me on this journey through the observable universe and beyond. The cosmos is vast, mostly invisible, and largely unknowable, but the part we can see is spectacular. And understanding just how little we've actually seen makes what we have observed all the more precious.